So now we're going to talk about line bundle. Remember we promised that at the end of this chapter we're going to reach a very exciting climax, right? We're going to see how the different things, the different manifestation of the Picard group, right? So one of these manifestation is the line bundle group, the group of invertible line bundle. Some author call the group of line bundle the Picard group, but I use the word the Picard group here to I use that for the group of devices made up by principal devices. Okay, so our plan is as follows. So first we'll define line bundle, right? Of course we need to first define the line bundle, and then we're gonna talk about, so then we need to construct and work with some explicit line bundles, right? We want to actually get our hand dirty and play with some real line bundles instead of just imagining the platonic form of line bundle. So we need to construct certain line bundles, but the definition of line bundle is not really useful. I mean, you could use it, but it's a bit cumbersome. So before constructing explicit line bundle, we want to recharacterize the line bundles in terms of transition functions. This gonna turn out to be useful not just for constructing line bundles, but later it will allow us to think of line bundle as cocycles. So that's gonna be the topic of the next section though. So right now we're just talking about line bundle. So after we have the recharacterization, we're gonna look at two line bundles that we know and love. Well, actually I lied. So you don't know them yet, but you know they are global sections. So these are the canonical bundle and the tangent bundle. From their name, you can guess what their global sections are gonna be. Now, so then after that, we have to get to that point where we start linking all of these different concepts together. So remember we say that we'll have isomorphism between the group of line bundle and the group of invertible sheaf. So we'll have to talk about the invertible sheaf associated to a line bundle. So given a line bundle, we are gonna associate an invertible sheaf. And then also we have the isomorphism between the group of line bundles and the Picard group. So that means that to each line bundle, I should also be able to associate an equivalent class of divisor. And that's what we're gonna do. So we'll define the concept of rational section of a line bundle, and we can take the divisor rational section. It turns out that it doesn't matter which section you pick, because all of the rational section are gonna have their divisors are gonna be linearly equivalent. Okay, so now let's define line bundle. So what is a line bundle? Well, roughly speaking, a line bundle on X is gonna be it's the following data. We're gonna have a space L and a projection pi from L into X. Yeah, but that's not enough. That's not just this map, but we need to put on it a line bundle structure. Roughly speaking, that's gonna be a collection of line bundle charts. So let's talk about line bundle charts, and then you can look up line bundle atlas and line bundle structures. But the key point here to explain is the line bundle chart. What is a line bundle chart? So how do we think of line bundle? Locally, we want them to look like a product of the complex line. So above every point P, we want the fiber pi inverse P to be isomorphic to the complex line C. So in other words, we want there to be, we want to cover X with open sets U such that pi inverse of U could be identified with, it's going to be isomorphic to C times U. in a way such that the fiber over every point P is going to be C. Now if we end the definition of a chart right there, that's not going to give us really interesting structure, because we can have really random, arbitrary trivialization, and that doesn't force structure to happen. So we want some kind of compatibility within between this trivialization. So, for example, if I have an open set V such that it has two different trivialization, which means that the fiber pi inverse of V will give in coordinates in two ways. Then I want the following requirement. So now notice that every point in the fiber over V, so for every point Q there is going to have two different coordinates, right? With respect to the first trivialization and one with respect to the second one. So then the map that sends the first coordinate to the second one, we can view that as a map on, say, linear transformation. On, say, we want it, so for at every point P, that map is going to be a linear transformation on C, and thus it's just a multiplication by some number. Now on the whole of V, that will correspond to a map, right? So on the whole of V, that will give a map, and that maps will send every point V in the fiber to something multiplied with V, and our requirement is that that maps is regular and nowhere zero on V. We want it to be nowhere zero so that we can invert it, because the two coordinates, they should be symmetric. We should not prefer one over the other. So if we can go from one to the other, we should be able to go back the other way. So on the edge of the fiber, the map should be an isomorphism of vector space. This map that translates between the two different coordinates, that map is called a transition function. And we can actually use them to give another characterization of line bundles, and actually in practice it's much more convenient to give a line bundle via the transition function. So those are charts, and then if we have compatible charts, then we form an atlas, and then when we have a really big, we have a maximal atlas, then we get a line bundle structure, right? Another way we can characterize this is we can say that a line bundle structure is an equivalence class of line bundle atlases, and we can define what it means for line bundle atlases to be equivalent. That just means the charts are equivalent, so you can glue them together. Now, then a line bundle then is just a projection from some L to X. So a line bundle over X is a projection from L to X together with a line bundle structure. Now before moving on to talk about the characterization of line bundles via transition function, we have to do the obvious thing, which is the mandatory thing after we introduce any definition, which is that we have to look at some examples, some basic, simple example, right? So what is the easiest and simplest example of a line bundle on X? Well, that would be the very appropriately named trivial line bundle on X, and I'll let you figure out what that should be. Now the next very important example of a line bundle, I call it a tautological line bundle. What we want to emphasize here is that the tautological line bundle, these are not, you have to understand this line bundle associated to a map from X to Pn. So it's not a canonical line bundle for a space X. That means it's not true that for every X there's this one tautological line bundle. Rather, the tautological line bundle is associated to a map from X to Pn. So for the same space x if we have different maps to Pn. Then we have different tautological line bundles associated to it. So alright, so let's describe this line bundle. So what do we do in describing a line bundle? Well, so far we only have the definition. We don't have the fancy recharacterization in terms of transition function. So we'll go to practice with the definition. So we first need to define this line bundle L as a set, and then we need to define the projection map from L to X, right? Then we need to give charts, and we need to check that the charts are really compatible. Alright, so let's define the space L. What is the set of this underlying set of this line bundle? Also, this is associated to some map from X to Pn, right? So let's call the map phi, and it's going to be given by f naught dot fn. So fi are meromorphic functions on X, not all zeros. Alright, so now we want to describe the line bundle L over X, right? So above every point P, we want to describe the fiber above every point P that should somehow be isomorphic to C. So how so? So we somehow should use the map from X to Pn, right? Well, so we want to understand it this way. So the map from X to Pn, really we can think of it as associating to every point in X a line, because remember, points of Pn are just lines in the affine space Cn plus 1. So we want to associate to every point P in X a line phi P in Cn plus 1. So we want to define the space L so that the fiber over P is exactly that line phi P. So how do we define L? Well, so this is a very common construction, common trick. We will define L to be tuples v comma P, where V is an element in phi P, right? So phi P is just a line in Cn plus 1. So we have points on that line. So each of these points will correspond to a point in the fiber. Now the projection map then is just projection to the second component. V comma P is going to map to P. Alright, so that's the set, and now we need to give an atlas, so we need to give local coordinate. Well, so we need to give a covering of X, right? And now usually we always cover X by f an open set. Yeah, the point here is that if X is, so we know, for example, Pn is best covered by the dxi, where dzi, let's say, where zi are the coordinate, projective coordinate of Pn. Now, to say that we have a map from X to Pn also means that we can put projective coordinate on X. The map was given by f naught dot f, and so we can think of the fi as a projective coordinate on X. So we can cover X by dfi. That would be the best choice. Notice that each of these dfi are really just the preimage on the V of dzi. Alright, so let's take a ui that is dfi. Now we need to give coordinate on the fiber of dui. Remember, a point in this fiber is an element of Cn plus 1 lying inside the line phi P, right? Now the line phi P, how would it look like if we have coordinate z naught dot zi minus 1, 1, so there's a 1 in the ith position, zi plus 1 dot zn, yeah? Because it's ith coordinate, it's going to be non-zero because we're over dfi, so the ith coordinate is going to be non-zero, so we can assume the ith coordinate to be 1. Now, so what are the points on the line associated to phi P? Well, so they are going to be tuples in Cn plus 1 that are going to be multiples of this, right? So they're going to be multiple of this. So because the ith coordinate is 1, we can check actually what multiple it is by looking at the ith coordinate. Yeah, so say the point alpha z naught dot alpha zi minus 1 alpha zi plus 1 dot alpha zn, we can just identify that with alpha. Yeah, so we identify the line alpha multiplied with the vector v, right, with a copy of c by sending each alpha multiplied with the vector v to alpha. Yeah, but in terms of the coordinate, we can say this is a map projection to the ith coordinate because the ith coordinate is alpha. Alright, finally we need to check that these maps are actually compatible. So what do we need to check to show that these are compatible? Okay, so let's find the transition map. So let's say we want to look at the coordinate on the chart dfi and dfj, so at some point that is on the overlap. So let's say we have a point in the fiber of the overlap, and that point has coordinate s with respect to vi. That means that its I coordinate is going to be s, right? So now it's I coordinate because this point corresponds to a unique number in the Cn plus 1. Now its coordinate with respect to j is going to be the jth coordinate. The j coordinate is just going to be s multiplied with zj. So the map is the map sending s to s multiplied with zj, right? And zj is viewing it as a map on x. Remember, we want to check that this is a regular function on x. Viewing it as a map on x is a map. We can write zj as fj over fi. So what we need to check is that fj over fi is regular on dfi cap dfj. Actually, not just regular, but nowhere vanishing, but that is true because on dfi cap dfj, fi and fj, neither of them are 0. So fi over fj is actually a unit in ox of ui cap dj.